In an earlier lesson, we learned the first postulate of quantum mechanics, which is that there is a wave function called the state function, or wave function, that contains all accessible information about the system. We learned that the wave function itself has no physical meaning, but we can extract the information from it. For example, we learned that the square of the absolute value of the wave function is a probability density function. By integrating this function, we can calculate probabilities of finding the particles of a system in specified locations. To extract other properties of the system from the wave function, we need to use operators. So we start by learning about operators first. An operator is something that transforms a mathematical function into another using a well-defined rule. We define an operator by writing an equation that says how it affects a function. An operator is typically represented with a capital letter with a hat. We read the example given here as a hat f equals derivative of f with respect to x. In other words, the rule for operator A as defined here is that if we apply it on a function, we get the derivative of that function with respect to x. What if function f is equal to x squared? Then applying operator A on it yields its derivative, which is 2x. A sum of two or more operators is just another operator that takes the sum of the result of each operator being applied separately. What does the sum of operators A and B do if it is applied on function f? The rule is this. Apply operator A on f and apply operator B on f, then take the sum. For subtraction of operators, a similar rule applies. Apply the operators on the function separately, then take the difference of the results. You can add or subtract two or more operators. Example. Suppose operator A takes the derivative of the function it operates on with respect to x, and operator B squares the function it operates on. What is the result if we apply the sum of operators A and B on x squared? Here's what we get. We apply A on x squared and get 2x. We apply B on x squared and get x squared squared. Then we add both results to get 2x plus x to the fourth. The product of two or more operators is applied starting with the rightmost operator. An expression like this, a hat, b hat, c hat, f, is interpreted as follows. We first apply operator c on function f. Then we apply operator b on the resulting function. Finally, we apply operator a on the function obtained after operator b is applied. Suppose operator A takes the derivative of the function it operates on with respect to x, and operator B squares the function it operates on. What is the result if we apply the operator product AB on x squared? We apply the rightmost operator first on x squared. B squares the function it's operating on, so B operating on x squared gives us x to the fourth power. Now that we have applied operator B, we apply operator A. Applying operator A on x to the fourth gives us the derivative of x to the fourth, which is 4x cubed. Note that if we reverse the order, we apply operator A first. This gives the derivative of x squared with respect to x, which is 2x. Then we apply operator B, which gives us the square of 2x. We get a different result, 4x squared. Here, in this specific case, we can see that the result is different if we reverse the order of operations. In fact, in general, the order of operations matters. We say that, in general, operator multiplication is not commutative. In general, operators do not commute. That is why it is important that we follow the rule. We apply the rightmost operator first. Raising an operator to the nth power simply means doing it n times. For example, suppose the d operator is defined such that applying it on a function yields the derivative of the function with respect to x. What function do we get if we apply d hat squared on sin x? D hat squared means apply D hat twice. Applying the rightmost D hat on sine x gives us cosine x. Applying the remaining D hat on cosine x gives us negative sine x. In quantum mechanics, we only use linear operators. A linear operator is one that obeys two conditions. First, if applied on a sum of arbitrary functions, you should get the same result if you apply the operator to the functions separately, then add the results. The second condition has to do with an arbitrary function multiplied by a constant. Applying a linear operator on the product should give the same result if you apply the operator on the function first, then multiply the result by the constant. A commonly used expression is to say that you can pull out a constant from the operator. What do we mean by arbitrary function? By this, we mean any function. It's possible for both conditions to work for a specific function, but if they don't for any function, then the operator is not linear. The two conditions that a linear operator must satisfy are often summarized with just one equation, like this one. In this equation, f1 and f2 are arbitrary functions, while c1 and c2 are constants. Anytime we have a constant times a function plus a constant times another function, it's called a linear combination of the two functions. If you apply a linear operator on a linear combination of arbitrary functions, you get the same result by first applying the operator on the functions separately, then multiplying the results with the constants, then adding the results. Suppose we define operator A as one that takes the derivative of a function with respect to x. Is it a linear operator? Let's see if the first condition is satisfied. We apply operator A on a sum of two arbitrary functions shown here as f and g. The definition of operator A says that we take the derivative of f plus g. The rules for derivatives are well defined. The derivative of a sum is equal to the sum of the derivatives. So, derivative of f plus g is equal to the derivative of f plus the derivative of g. But the derivative of f is the result you get when you apply operator A on f, and the derivative of g is the result you get when you apply operator A on g. Therefore, applying operator A on f plus g is equivalent to applying it separately to f and g and adding the results. Let's see if the second condition is satisfied. We apply operator A on a constant times some arbitrary function shown here as constant c times function f. Applying operator A on c times f means taking the derivative of c times f. The rules for derivatives say you can pull out the c when you take the derivative of c times f. But the derivative of f is what you get when you apply operator A on f. Therefore, the second condition is satisfied. A applied on a constant times f is equal to the constant times A applied on f. So, A is a linear operator. The answer is yes. Both conditions are satisfied. Suppose we define operator A as one that squares the function that it is applied on. Is it a linear operator? Let's see if the first condition is satisfied. We apply operator A on a sum of two arbitrary functions, shown here as f and g. The definition of operator A says that we take the square of whatever we apply it to. So we take the square of f plus g. From algebra, we know that the square of f plus g is f squared plus 2fg plus g squared. But f squared is what you get when you apply operator A on f, and g squared is what you get when you apply operator A on g. So, application of operator A on f plus g is not equivalent to applying A on f and g separately. We have this extra term, 2fg, which in general is not going to be 0. Therefore, operator A in this case does not satisfy the first condition. At this point, we can conclude that the operator is not a linear operator. We don't need to check if it satisfies the second condition, but let's do it anyway. Let's apply operator A on C times F, where C is a constant and F is an arbitrary function. The rule says to take the square of whatever we apply A on. So A applied on CF gives us the square of CF, which is equal to C squared times F squared. But F squared is what we get if we apply operator A on just F. So C squared F squared is C squared times A operating on F. This is not equal to C times A operating on F unless C is equal to C squared. The only way C can be equal to C squared is if C is equal to 1, but C can be any constant. Therefore, the second condition is not satisfied as well. Let's take a look at some common types of linear operators that we encounter in quantum mechanics. It would be a good exercise for you to try to prove that they are in fact linear. Replacement type operators are defined by specifying the variables that the function depends on, which ones to replace, and how. An example of a replacement type operator is the parity operator, which is typically represented by uppercase pi hat. It is defined this way. Applying pi hat on a function of x means replacing every occurrence of x by negative x. So if we were to apply it to, let's say, x plus 2x cubed, we do the following. We replace this x by negative x, and we replace this x by negative x. The net result is we get negative x minus 2 times x cubed. Multiplicative operators are the simplest types of operators. All they do is multiply the function by something, and it should be very easy to prove that they are linear. For example, we can define the x hat operator as one that simply multiplies the function it's operating on by x. So if we apply it on, let's say, sine of x, then the result is x times sine of x. Here are two properties of linear operators that are useful to know. The product of two linear operators is also a linear operator. The sum of two linear operators is also a linear operator. These should be fairly easy to prove. Here's how to start proving that the product of two linear operators is also linear. Assume that A and B are linear operators. Apply AB to a sum of two arbitrary functions and show that it satisfies the first condition required for linear operators. We need to show that applying AB to the two functions separately is valid. Remember that we must first apply the rightmost operator, so we first apply operator B on F plus G. Since B is a linear operator, we can distribute it to F and G. Now, B operating on F is just another function. Likewise, B operating on G is also just another function. Since A is a linear operator, we can also distribute it to the sum of these two functions. This gives us A operating on function B hat F plus A operating on function B hat G. Finally, we recognize that A operating on B hat F is the same as the product AB operating on F. Likewise, A operating on B hat G is the same as product AB operating on G. So the first condition is satisfied. You should be able to do the rest of the proof.